guys, it's me Claire, and today's video is on solubility calculations.
So today let's talk about solubility calculations. Now we know about saturated solutions. Those are solutions in which no more solute can be dissolved at a given temperature. But to make a saturated solution, we have to dissolve enough solute into a solution so that when more solute is added, it doesn't dissolve. It exists in a solid form, and that form we call a precipitate. So let's think about ionic compounds that are sparingly soluble, that is, they don't dissolve very readily. And one good example would be lead 2 chloride. So here we have a saturated solution of lead 2 chloride. And you can tell it's saturated because down here in the bottom of the solution you see some solid lead 2 chloride. So if you think about it, it's dissolving into solution and precipitating back out of solution. But these things are happening at once. If the system is sealed, an equilibrium can develop. That's equal rates. Remember the big idea of equilibrium. So here's an equilibrium equation showing the dissociation and precipitation forwards and backwards of the lead 2 chloride into its ions. So let's write a Kq expression for this, and we'll get the expression here as lead ion concentration times chloride ion concentration squared. Notice the lead 2 chloride is solid, and those are not involved in K expressions. So since this is not really a chemical system as much as a physical system, then we're going to rename this rather than Keq. We'll use a different kind of K, and it'll be Sp. So the Ksp will be the solubility product. There's the S and P, solubility product, equilibrium constant. So we go solubility product, there it is, Ksp. All right, so now let's determine the Ksp of lead 2 chloride. So here's an example. We get 1 liter of saturated lead 2 chloride, and we evaporate all the water away, and we recover 3.89 grams of solid lead 2 chloride. So we've got two things to determine. The first thing is the molar solubility of lead 2 chloride. Second is the Ksp of lead 2 chloride. So let's solve this simple problem and see how to make the calculations. Now the first thing we'll do is get the molar solubility of lead 2 chloride. That was part A. So here we have the mass divided by the volume, and we'll use here the molar mass of lead 2 chloride and determine that the solution was 0.0140 molar lead 2 chloride, and that's the saturation concentration at this temperature, whatever the temperature was. Remember, it could be different at a different temperature. In order to get the Ksp of lead 2 chloride, we're going to need the molar solubility, we just got it above, and we'll need the ionic dissociation equilibrium reaction. So let's make sure we have that written down. In it again, we had above, here it is lead 2 chloride, making the lead 2 plus ions and these 2 chloride ions. So the Ksp expression will be concentration of lead 2 plus times concentration of chloride ion squared. Notice the 2 in the chloride ion gets you a square. Now we need to get these ion concentrations, and we know the lead 2 chloride was 0.0140, same with the lead and the chloride ion, because it's 2 to 1, the other ones would be twice as much, 0.0028, or 0.028, I'm sorry. Notice that the 2 gets used twice, once to get the ion concentration and once for the square. So here we have the Ksp expression, and calculating this all up nicely, we get 1.1 by 10 to the minus 5 at this temperature. Okay, that's it for our example. Sometimes we also want to determine ion concentrations or molar solubilities using Ksp values, so going backwards the other direction. Here's a good example, and the question that we have here is, including this idea, and it's a little bit of an extra twist on it, what mass of copper 2 iodate is required to saturate 400 ml of solution at 25 Celsius? So first we're going to need a Ksp expression for the copper 2 iodate, and here it is. You have the typical dissociation and precipitation reactions, and we'll need a value for the Ksp. So we'll go here to our table, look up copper 2 iodate as 6.9 by 10 to the minus 8. Okay, so although not necessary, it's sometimes easier to introduce a variable to solve for these ion concentrations, and let's say that the copper iodate, copper ion, and iodate ions will be an x to x to 2x ratio. So here's the logic. Every x particles of copper 2 iodate that dissociate will release x copper 2 plus ions and 2x iodate ions. So all good there. That's the idea why we can use these variables. Here we have the Ksp expression. The copper ion times the iodate ion concentration squared. These will be x and 2x, again squared here. Little algebra gets you this as 4x cubed. Now we need to solve for x. That's what we're looking for after all. So a little more algebra. Take the cube root of Ksp divided by 4, put in all the values, and we get this number here of 0.00258 molar. And that's the saturation concentration of the copper ion. And since it's also the pre-dissociated concentration of the copper iodate, then we can also use this value for our calculations of the mass of the copper 2 iodate. So here we have it. It's 0.400 of a liter of the solution. In every liter, we have 0.00258 moles. Every mole of copper 2 plus ion came from 1 mole of copper 2 iodate. And here we have the molar mass of copper 2 iodate. Check that everything works. You get the mass of copper 2 iodate. And it turns out to be 0.427 grams of copper 2 iodate that was in there. Okay, so those are the most basic solubility calculations. The first one is calculate Ksp from the molar solubility, and second, calculate the molar solubility from the Ksp. In our case, we also calculated a mass just to refresh some of our unit analysis skills, but everything you need to know is right in there. So thanks everyone. It was quick. See you soon. Have a look at the next 2 videos for more. Stay tuned for our next topic, lesson 15, subtleties in solubility equilibrium.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.